Hey everyone, Mr. Fransky here one more time with a video about complex numbers going just a little deeper. So remember, complex numbers, those are those numbers that look like a plus bi. A and b are both real numbers, and I is that imaginary unit, the square root of -1. That's our I value. So I is an imaginary number because we can't have a square root of a negative number, and so we need it though to solve some equations. Speaking of which, let's take a look at one. So if we wanted to solve this equation, it's equal to 0, we could try graphing it, and if you graph this guy, you actually get something that looks like this. The vertex is at 1, 6, right there, and it opens upwards. So we have an issue solving for the zeros because it never goes to 0. And if you tried to factor it, you can do the xbox. Well, 7 times 1 is 7, and then our b value -2. You will never find two numbers that multiply to 7 and add to -2. You can try, but you won't be able to. And so what we have to use is the quadratic formula. So see who out there remembers the quadratic formula. You might remember the story that I told. The negative boy couldn't decide whether or not he wanted to go to the radical party. He decided to be square, missed out on 4 awesome chicks, and it was all over at 2 a.m. I made that line a little bit messy. Let's see if I can make it a little bit better. All over at 2 a.m. So negative b plus or minus square root of b squared minus 4ac all over 2a. Biggest mistake people usually make is they don't put the entire b squared minus 4ac under the square root sign, and you'll end up with a weird answer if you do that. So what are these things? Well, a, b, and c come from the standard form here, ax squared plus bx plus c. So in this case, my a is 1, because I have my coefficient in front of the x squared is just 1. My b is -2, and my c is 7. So I'm just taking a, b, and c from my equation up top here. And I'm just going to plug those into the quadratic formula. So negative b is negative -2. That's positive 2, plus or minus the square root b squared minus 4ac. So that's 4 minus 4 times 1 times 7 is 28, all over 2a, which is just 2. So that's 2 plus or minus the square root. 4 minus 28 is -24. And that's all divided by 2a, which is just 2. So square root of -24. So we have a square root of a negative number here, so we need our imaginary numbers. So this is going to be 2 plus or minus I times the square root of 24. Remember, if we have the square root of a negative number, we can just pull out an I. So now it's positive 24, all divided by 2. Well, square root of 24, let's see, 24 is 4 times 6. So 4 is a perfect square. Remember, we want to see if we can pull out a perfect square from 24. So this is 2 plus or minus I times the square root of 4 times the square root of 6, all divided by 2. I'm try to do this without running out of space here. So we have 2 plus or minus I times 2, so I'm going to write that as 2I, times the square root of 6, all divided by 2. Now we can split that up. I'll put that over here. We can split that up across the plus and minus because it's a fraction that has a single denominator. So we can write that as 2 over 2 plus or minus 2i root 6 over 2. Well, these cancel to 1. And then it's plus or minus 2 over 2. Those cancel as well. Root 6 times I. I'm going to write it like that. Root 6 times I. So now we're in a plus bi form. So our two solutions are 1 plus root 6i and 1 minus root 6i. Well, that's kind of cool how that worked out. We had the plus and the minus. And let's see if that always works. So if that's kind of some kind of a pattern. Well, remember the quadratic formula. Negative boy, couldn't decide, radical party, b square, missed out on 4 awesome chicks, all over at 2 a.m. So there's an important part in here, so important that I'm going to change my ink color just so we can see it. This guy right inside of here, this b squared minus 4ac, there's a special word for that. It starts with the d. It's called the discriminant. Let's see if I can spell it right. Discriminant. I think that's right. b squared minus 4ac. And it's called the discriminant because it determines or discriminates against different solutions. So if b squared minus 4ac is a negative number, if it's negative, so if b squared minus 4ac, is less than 0, then we're going to have imaginary solutions. Imaginary or complex solutions. So if we have a discriminant here that's less than 0, we're going to have imaginary solutions. Like in our last slide, we had a discriminant that was negative 24. Well, if it's negative 24, we're going to have an I in there. And the reason we get this pattern here, this 1 plus 6i, this 1 minus 6i, is because if we split this up, it's just negative b over 2a. I'm stuck with this color now. Let's go back. I'm going to use something else. I don't like that other one. Let's do green. So we have negative b over 2a plus or minus. And then if this is less than 0, then we can pull an I out and turn it into be positive. So it's going to turn out to be the square root of 4ac minus b. Because if I pulled out that I, that was my negative that I pulled out of it. So now this is going to be positive. 4ac must be bigger than b squared if this is going to be negative. So I flip it around, and that's over 2a. So in a plus bi form would be negative b over 2a plus or minus square root 4ac minus b over 2a all times I. So you see we have the plus and minus there. And so we're going to get the positive one and the negative one. These things are called complex conjugates. Complex conjugates. So a little bit of vocab here. The discriminant is b squared minus 4ac. Complex conjugates, just if you have a plus bi, then the complex conjugate is a minus bi. So that's always going to happen. If you have a complex solution, like 1 plus 6i, then the other one, the conjugate, 1 minus 6i, is also going to be a solution to that quadratic. So we don't really have to worry about the letters here. I just wanted to show you that always it will work out where if one of them, the positive, is a solution, then the negative will also be a solution. So for example, if we find out that 2 plus 6i is a solution to some quadratic, or a 0, right? It says 0. Then we know that 2 minus 6i is also a solution. Also a solution. It has to be, because of the way that the quadratic formula works. So discriminant and complex conjugates are words we're going to see a little bit later on. So last thing we're going to talk about with complex numbers is the division. Last video we talked about multiplying by a constant, we talked about multiplying them together, we talked about adding and subtracting, but we never talked about division. So we're going to start with an easy example here. 4 plus 6i over 2. So this is just like dividing by a constant with a fraction that has variables across an addition sign. We can write it as 4 over 2 plus 6i over 2. Well, 4 over 2 is just 2. The 6 over 2 cancels to a 3, so it's 2 plus 3i, and we're done. So that works really well with a constant on the bottom there. We just split it across the addition sign, because you guys are used to going the other way, where you have to find a common denominator, right, to add the tops across. But here we're just splitting it up. We're splitting it up across the addition sign on the top. So we just split it up with the 2 on each side. But what's harder is if we have a complex number on the bottom, because this is basically like having a radical or a square root in the denominator, right? And we know that's a no-no. If you have like 1 over the square root of 2, you have to get rid of it by multiplying by square root of 2 on the top and on the bottom, right? That'd be root 2 over 2, important trig number. But in this case, our I is the square root of negative 1, so we have to think of some way that we can get rid of that I on the bottom. So basically, there are no I's allowed in the bottom. No I's allowed in denominator. So we want to be able to write this in a plus bi form. That's usually how you hear it. They say they want you to write this in a plus bi form. And we can't do that because we have an I on the bottom. So how do we get rid of it? Well, there's a pretty cool property of conjugates that we're going to take a look at here. So let's see if these conjugates can help us out. To my green here. Oh, there we go. So these conjugates, the idea of complex conjugates, might be able to help us get that I out of the bottom. So let's take a look. So if we're looking at 1 plus I, think the complex conjugate, remember, we just switched that sign in the middle. So the complex conjugate of 1 plus I is 1 minus I. Let's take a look at what happens when we multiply those two together. So multiplying 1 plus I times 1 minus I. We need a box for that. So we have 1 plus I, and we have 1 minus I. 1 times 1 is 1. 1 times I is I. 1 times negative I is negative I. And negative I times I, let's think about that. Negative I times I would be negative I squared, which is negative 1, which is 1. So we have a 1 down here. So now when we add these all together, I minus I, those go away. So then I'm just left with 2. Well, that's kind of cool. And that gives me a number that has no i's in it, which might be helpful for our denominator. And this always works. Check this out. If you have a plus bi, and you have a minus bi, let's see what we get. A times a is a squared. A times bi is just abi. A times negative bi is negative abi. Bi times negative bi is going to be negative b squared I squared. Well, I squared is negative 1, so it's going to be positive b squared. ABI, negative ABI cancel, so we're always left with a squared plus b squared. Well, that's kind of cool, because we said that a and b are always real numbers. If a and b are always real numbers, then this is always going to be a real number. So if we always have a real number here, we have a way of transforming a complex number into a real one. So let's see if we can solve that. Give myself a little bit more room here. So we need to be able to get that I out of the denominator. Well, we just found out if we multiply by complex conjugates, we'll get a real number. So let's do 1 minus I on the bottom. And we also have to do it on the top. So we haven't changed the fraction at all. It's like multiplying by 2 on the top and the bottom or something if you're using a common denominator. So when we multiply this, on the bottom, we just found out we'll have 1 plus I times 1 minus I. We know what that's going to give us. It's going to give us 2. So on the bottom, we're going to have 2. It's always a squared plus b squared. So 1 squared plus 1 squared, which is 2. That's where 2 comes from. Now on the top, we'll have to make a box. We have 6 plus 10i, and we have 1 minus I. So we have 6, we have 10i. 6 times negative I is negative 6i. Negative I times 10i is negative 10i squared, which is positive 10. Right, and that gets us positive, let's see, 16. And then 10i minus 6i is plus 4i. So on the top we'll have 16 plus 4i. Now we can reduce that because 16 over 2 is 8. Gosh, I'm running out of all kinds of room here. I'll go over here. 16 divided by 2 is 8. And then 4i over 2 is 2i. So we have 8 plus 2i is the result of that division. And we're given it in a plus bi form, which is excellent. Okay. So, how does this fit? All this complex number stuff. Why the heck are we learning this in the middle of a chapter about factoring and finding zeros? Let's take a look at what happens when we factor each of these equations. This first one, none of these have middle terms, so we can just solve these by using square roots. If we add 9, we'd have x squared. So if we set this equal to 0, let's say, x squared equals 9. And then take the square root of both sides. Remember, we take the square root, you take the positive and the negative. So x could be 3, or x could be negative 3. So I just found the zeros. I just found the zeros because I set it equal to 0. So factor theorem tells me the factors are x minus 3 and x plus 3. So if I can find the zeros, I can just factor it by using factor theorem. Excuse me. This next one's very similar. Set it equal to 0 to find the zeros. So then add 5 to both sides. And we'll have x squared equals positive 5. Now we take the square root of both sides. Gives us 2 answers. So we have x equals positive or negative root 5. So then factor theorem tells me I can factor this. I'll have x plus root 5, x minus root 5. So these root 5 things are a little weird because we usually see whole numbers or integers, but it still works. Now the last one is really why we're learning about complex numbers. If I have x squared plus 36 equals 0, I can subtract 36 from both sides. And I have x squared equals negative 36. But then when I take the square root, I need that negative square root of negative 1 value. So once again, remember I can have a plus or minus there. So I would have x equals plus or minus I root 36, which is plus or minus 6i. So then my factors, x plus 6i, x minus 6i. We are out of time, but give the homework a shot here. Solutions are on Moodle, and I'll see you tomorrow.